Okay, in the previous video we talked about the multiplication and division of surds, and this video will be a continuation of that using a rather tougher example. And this video would also consider using the prime factorization to make things really simple. If you are struggling to find the multiples, that will give you the set of this and then the set of these. Everything will be covered in this video, so make sure you watch it and then watch it thoroughly. Make sure you also understand the concept very well. If you struggle to do so, rewatch the video. I'm sure the explanation will be easier for you to go about it. How do you represent this value in such a way that you can know that it will be a number root something? Or an easier way to go around it is writing the number in the prime factors form. And so we take all of these numbers and represent them in their prime factorization form. Let's take 162 for instance. 162 is 9 times 18. 9 times 18 will give you 162, and I could tell 162 can be divided by 9 because if I add the numbers, if I add 1 plus 6 plus 2, the result is 9. And the division of 9 rules is that if you add all the numbers and the result is divisible by 9, then the number can be divided by 9. So me adding 1 plus 6, which is 7, plus 2, which is 9, tells me that 9 can divide this number. When I do that division, the result is 18, meaning 9 times 18 gives me 162. One can literally also use a different number. 162 is also 3 times 54. But the key thing to recognize is that after writing the prime factorization of this, regardless of the multiplication method you use, you come up with the same prime factors, and we consider this under the factorization of prime numbers, and the video is linked in the description. So if you struggle to understand this, please watch that video as it considered this issue thoroughly. Right, now how do we go further? These are not prime numbers, and we want to make sure that all these numbers are expressed in their prime numbers form, because we said prime numbers are the building blocks of all numbers. You can literally build all other than prime numbers by multiplying prime numbers. So because there is not a prime number, we can still go further. 9 is 3 times 3, and 3 are all prime numbers. Of course, it's just the same number. 3 is a prime number, so we are done with this. How about this? This is not a prime number, so we need to go further. 18 is 6 times 3, or however you want it. You can choose 9 times 2, but then you get the same prime factors like this. This is also a prime number, so we are done with this. How about this? It is not, so we can go further. 6 is 2 times 3. You realize now we have all of it in their prime numbers, and we could tell we have the prime numbers 3, 3, 3, 3, and then 2. So how many numbers we have? 1, 2, 3, 4, 5. And if you look at these two, we can represent them as 3 squared. The key goal is that if you represent numbers as squared under a square root, we know it cancels out. So it is good to strive to get numbers as squared, and that is what this method seeks to do. When you represent the numbers in their prime factors form, and then you see a number that appears twice or more, you rewrite them as powers of 2. So in this case, you have 2 3's, and so we will represent it as 3 squared. We have another 3 and then another one here, so we can represent these two as another 3 squared, and then this would be just 2. So we take these two and then this. These are the prime numbers that when you multiply we get 162. If you like, you can check. So we are done with this, and multiplying this in the index form, you see 3 squared times 3 squared times 2. That is these numbers we have just represented here. If you multiply this, you are going to get this. Great. Let's take 32 too. 32 can be represented as 16 times 2. 2 is a prime number, so we are done with it. 16 isn't, so we reduce it further, and then we get 2 times 8. This 2 is also a prime number. We focus on this. This is a prime number. We focus on this. And we have represented 32 in prime numbers. If you look carefully, you can see that we have these two we can represent as 2 to the power 2. We can represent these two also as 2 to the power 2. And this one wouldn't have a power of 2. So this is how we represent it. 2 to the power 2 times 2 to the power 2 times 2. Recognizing that if this under a square root, it will cancel out and have our numbers to ourselves. So these two give us this, these two give us this, and this odd one is this. Okay, 98 is 2 times 49. 49 is 7 times 7. We didn't go that far. We have our prime numbers already. Now we can represent this 2 as 7 to the power 2 times 2. And that is all we have here. Good. Lastly, we focus on the 8. And the 8 is 4 times 2. We have our prime number here. 4 is 2 times 2. You realize you have 2, 2, 2. We can represent these two as 2 to the power 2, and this will remain. Okay, so 8 now becomes 2 to the power 2 times 2. So instead of writing 162, 32, 98, you rather replace them with these prime factors. These prime factors. Alright, now that brings us here. If that is the case, then we represent 162 as 3 to the power 2 times 3 to the power 2 times 2. This is what we go after prime factorization of it. Okay, now the same thing happens here. For 32, this is what we got, 2 to the power 2 times 2 to the power 2 times 2. For 98, we got 7 to the power 2 times 2. And then for 8, we got 2 to the power 2 times 2. All of them under their square roots. Now to make things clearer, we separate all of them under their own individual square roots. So this is what we have here. It's the same thing, just that we've separated it to make things clearer for you. Right, so 3 to the power 2 is it, 3 to the power 2, this is it, and then square root of 2, this is it. Right, we do same for the others. 2 to the power 2 is this, another 2 to the power 2 is this, and then times square root of 2. All of this is what we have represented as this. Nothing has changed. We have just separated it for easier identification. The same thing, square root of 7 square times square root of 2. And then we don't forget our denominator, which is square root of 2 times square root of 2. Sorry, this is square root of 2 squared. Now things becomes very easy because you see that square root of 3 squared is 3. Square root of 3 is also 3 because this cancels this. That leaves us 3 times 3 times square root of 2 for this. This expression now becomes this because these two cancel, these two cancel. This doesn't have a power of 2, so it remains. Similar thing happens with this. 2 to the power 2 becomes 2 to the square root of 2 to the power 2 also becomes 2, and then the last one doesn't have a power, so it remains. How about 7? Same thing happens. Good. When we come here, this also cancels this one out, leaving this alone. You can see that things are becoming clearer. All of them have a square root of 2. Now we are not done yet. You can still go further. We have 3 times 3, which is 9. So we get 9 root 2. We have 2 times 2 here, which is 4 root 2. Now 7 times root 2 is 7 root 2 divided by 2 root 2. Alright. Do you see anything here? Now everything is simplified. We have 9 root 2 plus 4 root 2 minus 7 root 2. All of them have a like term, which is the root 2, meaning we can add and subtract them. 9 plus 4 plus, 9 plus 4 minus 7 is 6. 9 plus 4 is 30 minus 7 is 6 root 2. Then over 2 root 2. Can we see anything? Yes. 2 and then 6, square root of 2 and square root of 2. We know these two will cancel out. Then this can also divide this by 3. And that is what we see here. And so we have 3. All of this complex thing, the answer is 3. Because 2 cancels 6 3 times, whilst the square root of 2 cancels the square root of 2. And that is the answer for this. Whenever you have a set expressed in a complex form like this, rewrite them in the prime factorization, and that is what this video took you through. So it shouldn't be difficult from now on. Then whenever you see that there are powers of 2, make sure you represent them. If you see the number happening for any prime numbers, try representing them as to the power of 2 until it is exhausted. Now from what we did, it tells that if you write the prime factors of numbers and then you have even number of prime factors, it will eventually become an unsaid or a rational number. But if it is an odd number, then a said would happen. This example seek to clarify all of your worries. So whenever you face a complex set, try using this method to get your answer. Alright guys, make sure you subscribe, you share, you like, you comment. As you are getting value, you make sure you help us to also grow the channel as well. Don't forget to subscribe and then tell your friends about it. Make sure you help them also get value from this channel. Okay, see you in the next one.